Okay, let's get started. So today we're introducing some new material and whoops, that doesn't happen automatically. And the material is going to help us be able to calculate voltages on the system. And these are exact voltages. And what we'll do with those voltages is we'll be able to calculate power flows, currents, and all that stuff once we know what the voltages are. So what we're going to do is determine the need to calculate. So we just talked a little bit about why we need to do that. We're going to write what are called power balance equations. And the reason why we have to have power balance equations is essentially we're going to be solving some nonlinear equations. So we'll talk about why we need to develop these power balance equations. We're going to use math techniques, right? Because we're solving nonlinear equations. And we're going to use the Newton-Raphson technique to actually solve those linear equations. And then we're going to develop a Jacobian. Sometimes people call it a sensitivity matrix for multi-bus systems, meaning, you know, 2 bus up to 2 million buses, essentially. So again, everything is going to be in a matrix. So one of the questions is why bother doing this? Well, there's a tremendous amount of effort that is done on a daily basis to make sure that the system, the power system, is stable. And what is a stable power system? Obviously, we know that voltages are within tolerance, frequencies are in tolerance, but then we also have this thing called NERC, N-1 contingency, and NERC sort of has been given authority by FERC to set the rules for providing power and how the utility or the power system is operated, at least in most of North America. And one of the things is because these are electrical systems and stuff happens, right? You got long transmission lines that are exposed to the environment and, you know, you can't always protect those. We've got to assume worst case that we can take any single piece of equipment, and I don't care what that piece of equipment is, any piece of equipment has to be able to be taken out of service, and the grid has to be able to survive that. It may not be in a happy space, but it has to be able to survive taking out that worst piece of equipment. And that's what's called N-1 contingency. So you have N, which is the actual number of operating either lines or generators or whatever. And if you take one of those out, the system can still operate. And so one of the things that system operators or system planners do is they'll run analysis after analysis after analysis, trying to figure out, is there an operating condition, meaning power flow in one direction, or too much load in another location, or this transformer out of service that would jeopardize this N-1 contingency criteria. And if it is jeopardized, then what you have to do is you have to back off the system operation so that you are N-1 contingent. So a perfect example of this was a couple years ago in Texas. Do you remember Texas in February where they had blackouts? You might have heard Ted Cruz went to some place and there was a lot of political blowback. I'm not saying that as a bad thing about Ted Cruz. I'm just saying that was that's where you heard about it. Well, the reason being is because it was cold. It was much colder in Texas than many of these people had predicted. And so they didn't have a lot of generation capability as they normally would. And so what they did is they actually had to trip off load. But if people would have dug down into it, ERCOT, who was the grid manager for Texas, actually had spare capacity in their system. They actually could have operated more load if they felt comfortable to, but they still needed to maintain this NERC N-1 contingency. So even let's say they had 50 gigawatts of capacity, they might have had to have 5 or so, I'm just saying those numbers, I don't know exactly what the numbers are, but they might have had 5 or so spare contingency so that in the event something happens, that the system can still continue to operate. So you're never operating at the limit of what your system can support because you have to have this N-1 contingency. And you'll actually see there are days like under extremely hot days or when there's very little generation, they actually issue all kinds of alerts and warnings saying, don't touch anything, don't make any changes, please stay away from the grid because we are in a really serious condition, which really starts to push the N-1 contingency. So it behooves us to envision a system or design a system that isn't so reliant on one piece of equipment that, you know, if it goes away, then we have some real problems. You can design a system for that, but that becomes very expensive. So it's a balancing act, right? Design the world's best system, but it's going to cost a lot of money. Design the world's cheapest system, but it's not going to be reliable. Try to find something in the middle. And so what we're doing with a load flow is essentially doing contingency analysis after contingency analysis and taking a bunch of systems out of there once at a time. You can also monitor the system everywhere you want, and then you can actually see if your results that you calculated match what's actually out in the field. That's called state estimation. So you can actually add a little more accuracy, but it does complicate the system, the analysis a little bit. And then the contingency capability, how do you do that? Well, if I take a transmission line out of service, how do I do that? I just modify my Y bus, right? If there's no connection between bus 742 and 816, then my contingency analysis is to make the Y bus location for that equal to 0. So you can do automated contingency capacity very quickly if you take advantage of the benefits of Y bus. And so how do we figure out which generators to run? It's not always the lowest cost gets on and meets the load. Again, if that generator can make power extremely low, then yeah, run it full out until such time it starts to challenge the NERC N-1 contingency. So you can't make the system unreliable and still make it cheap. So that's why we say lowest price doesn't always win. Sometimes you have more capacity to go and you could sell it for cheaper, but because you're being pushed too hard and the system could fail if you trip offline, then we won't dispatch you for more power. And then what about when a fault does occur? We have to assume that faults do in fact occur. And so we need to analyze a system for fault conditions. And every system has to be designed so that it can tolerate the worst case fault. And so one of the things you want to do, and there's a couple of different ways to do this, but one of the things you can do is actually calculate all the system bus voltages and calculate fault currents from there. Some people do what's called a flat start. They assume like a 1.03 per unit voltage and do fault analysis from there. So they would just assume all the bus voltages are 1.03, and then it's an easy calculation. But if you want to get more exact, you would need to do what we call a power systems analysis or a load flow. Let me move this out of the way because it's blocking. I can't see it. So the load models, and we talked a little bit about this early in the semester, the load model is something that we have to consider. So we talked about constant impedance or constant power. And we typically like to have constant power if we can, because again, the customers are paying for the power that they're using. So if we treat it as a constant load, or it acts like a constant load, a constant impedance, then as the voltage drop, the load decreases. And as a result, we end up not making as much money. So why is that important? Because we want to try to maintain those voltages within reason, and we want to make sure that the frequency is pretty much perfectly 60 hertz. Out of the two, usually frequency is the one that deviates the least. Voltage usually deviates the most. In fact, I've never seen frequency deviate by more than like 0.1 hertz unless some really wacky fault condition happened. So loads are being flicked on and off, right? You're turning your light switch on, you're turning it off, you're running your garbage disposal, you're running your dishwasher, your oven. Sometimes you're doing that, sometimes you're not. So you don't necessarily have all the specific information about individual loads. So you aggregate them. You put them all in one lump, and then you define it as a P and a Q, or a P and a power factor, or an S and a power factor. And those are estimated typically for what we would do. So we would do a look ahead, and we would predict what we think the load is going to be, obviously based on previous data, so that we can figure out what to dispatch and go from there. But again, we simplify things and assume that the load is lumped at a bus, and we're not going to worry about every little toaster or whatever that's in your house. We already talked about constant power, constant impedance. Motors, we typically treat them as constant power, because one of the things about a typical induction motor is as it starts to slow down, within reason, it actually draws in more power. So if you try to drop the voltage, it would slow down, but then it's going to increase the amount of power, so it backs back, it increases it back up. So it's a mechanical load, and usually the load is what dictate what it needs, not the speed. Our generator model is just an ideal voltage source in series with an impedance and a resistance. And that's a steady state model. It's not time varying. And we'll learn about time varying when we get to it. We're also going to focus mainly on generators being synchronous machines and not inverter-based generators, although that's becoming more and more prevalent. And the reason why we focus more on generators is because still most of the fault current in the North American grid is from synchronous machines. So those will actually dictate a lot in terms of what the fault current actually looks like. You can go ahead and make it so that it's not a steady state. So if you want a time varying model, because over the time of a fault, the fault current levels will change because you have a decaying exponential. Anytime you see an inductor, you can see that you have some energy stored there and it can decay away. And so you actually will drop your fault current as time progresses on in the fault. What are the other models that we have? Well, we just covered transmission lines, right? We did the pi equivalent, and then we did the ABCD parameters. We did the transformer model, where we already did open and short circuit tests to come up with an equivalent set of resistors and inductors. Any cap banks, and there are tons and tons of cap banks out on the system, those would be modeled just as capacitors, right? There's nothing fancy about those. You don't see a ton of what we call chokes or inductors. Sometimes they're called line reactors. The difference is in the terminology is what it's used for. So the only time you typically will see like a line reactor is what I've seen them on is typically distribution circuits. So normal distribution, like if you go to your house and you look at your breakers, most of those breakers are rated to interrupt 10,000 amps. So if you have a distribution circuit that can put out 50,000 amps, then nobody's home would survive a fault, right? It would catch on fire because the breakers could not open. And so like I did a project many, many years ago for Harvard, and they had in Boston or Cambridge, they had massive amounts of fault current. And so one of the resolutions there was actually to put incoming reactors that knocked down the amount of fault current. And you didn't put a resistor because a resistor is consuming real energy, right? It's wasting joules because it's just generating heat. Where a reactor is going to knock the fault current down, but it doesn't actually waste any energy, right? Because the power is sent back. So that's pretty much the only time I've seen reactors actually in the power system. You will also see them for like communication signals where they act as a line trap. And sometimes you'll see them at night being into the system because the voltage are trying to reduce it. But for the most part, they're pretty limited when you see reactors. Resistors are not that common as well because, again, it's wasting energy. So why would you put a system out there that you're not getting paid for? You do see resistors on neutrals in many cases, or sometimes you see load banks with resistors, but capacitor banks way more often than any of the other ones. We also can model nonlinear stuff, but that's not the purpose of this class. But we are seeing more and more nonlinear devices that we need to consider with our models. So now we can do a representation of our system. We have a model. Now let's actually analyze it. So we're going to do what's called a load flow or power systems analysis. And in fact, the actual result of a load flow, you think, hey, we're going to calculate the flow of load. No, the actual outcome, the first outcome of what we're going to be doing is actually calculating bus voltages. Once we know the bus voltages and the model of the system, then we can calculate power flow. But the ultimate output of our load flow analysis is just tell me what all the voltages are at every single bus, both magnitude and angle. So we'll determine bus magnitudes and angles of bus voltages, which will allow us to calculate currents, right? Because we did that in one of our first homeworks. We had voltage at bus 1, voltage at bus 2, the impedance of the line. We can calculate the current pretty easily there. But what makes this really difficult is our models tend to be nonlinear. What do I mean by that? Because S equals P plus JQ. It is not a linear relationship. So we actually have to solve our power flow using nonlinear analyses. And have you all done nonlinear analysis up to this point in your college careers? Laplace? No, that's linear. Almost everybody here has, they just don't realize it. Anybody here taking a semiconductor course? Op amps or BJTs or transistors or anything? What do you assume when you're using your op amps or transistors or BJTs? You have small signal operation, right? So you linearize about a very small point. So you pick a point and you assume small signal operation. You're not going to deviate very much from that point. And as a result, you can analyze with linear systems. We're going to pretty much do the same thing, but we can't, like like you pick a Q point, or you look at a BJT and you look at the curve to see, based on a biasing current, you can see what the current flow or the base to the collector to emitter voltage is going to be. We can't look at a curve for this because this would have a curve with millions and millions of dimensions. It's just not practical. So we got to do it with math. So here's our technique. Actually, this is not our technique. This just shows you if the system is linear a lot. So a linear system is you can take any input, and if you get an output by taking the individual inputs and you get that same output, then the system is linear. So I've got a function h, and I've got two different inputs, u1 and u2, and then I just multiply by some coefficients. And if the input to the system, the combined input of those, the combined input, meaning the sum of those two, is exactly the same as the individual output, so h u1 times alpha 1 plus h of u2 times alpha 2, then it's a linear system. So that's the proportionality. And then we also need the concept of superposition, which again, I can put c times x1 plus x2 in there, or I can just put cx and I get the same result. So the first one, cx, is a linear system. The second one is not, because if I plug in cx squared, you can see if I plug in x1 plus x2 and square that, I do not get c times x1 squared plus c times x2 squared. So even a simple equation like h equals cx squared is nonlinear. So I would need a little bit more work. And actually, we'll actually figure out how to use or write code, I think similar to how your calculator works, because your calculators work on the same approach, which is how to calculate square roots. So here's another example of a simple power system, right? So this is a simple circuit here with some resistors. We got two power supplies and three resistors. And we can go ahead and solve for any parameter, voltage or current in this case, through R3 by solving for the current I3 as a result of V1. And we turned off V2. And then doing the same thing again, turning off V1, solving for the current I3 through V2. And then when we're all done, add them together. Okay? And that applies for resistive circuits, inductive circuits, capacitive circuits, or the combination, because those are linear systems. Where it doesn't apply is if my third resistor in the previous circuit is no longer a resistor. It is a constant power load, which means its resistance is varied depending upon the applied voltage. So this gets to be a lot more complicated of a problem, right? Because that R value is changing all the time. So how about this problem? X squared, f of x equals x squared minus 2. Well, we can plot it, right? So what we're going to do is we're going to do root solving. So we're going to set our f of x and set it equal to 0. And we're going to solve for x, and we can do that manually, or we can do a plot. And if you look at the curve, you can see that where it crosses 0, right here, and here, I don't know why that erased, where it crosses at 0, that's a valid solution, right? And we can see that that is, just by looking off the curve, that's plus or minus 1.414. Either one of those is a valid solution. Now, if we monkey with that equation a little bit, and instead of x squared minus 2, we go x squared plus 2 and set that equal to 0, we don't have a real solution, right? We can't plot anything that's going to give us a real solution. We can end up with a solution, but it has 1.4 plus or minus 1.41 j, right? Would be the solution to that. And we won't be able to have plus or minus j as our solutions when we do power systems. Here's a simple case where we have a constant power load, and this is just a simple series circuit. We have a 9-volt battery and a 1 ohm resistor feeding an 18-watt load. So what we're going to do is solve our nonlinear equation, and we know that I squared times R, and that's our load, not R, but our load, has to be equal to 18 watts. So my current squared is, or my current is 9 divided by that 1 ohm resistor plus the load resistance. Multiply that by our load and set that equal to 18 watts. And there are two valid solutions. One is 2 ohms and one is 0.5 ohms. Either one of those would work for this particular case. And so when you see when we do our Newton-Raphson load flow, we're actually going to see where we do have cases when we can have multiple valid solutions. It's just one of them may not be realistic. So now we're ready to apply Newton-Raphson load flow, or algorithm, I should say. And it's the concept of sequential linearization. So you're going to linearize about a point. You're going to do some work and see if you're close to the final answer. If you're not close, you're going to linearize about a new point, do some work, see if you're close to the final answer. If you're not, rinse and repeat. So it is essentially an iterative process. So when you're doing a load flow, you have to do iterations. And you remember at the beginning of the semester, I said MATLAB, it would benefit you to use MATLAB. Why do you think I said that? Yeah, you can set up while loops in MATLAB, right? You can do very simple coding. You can do a while loop or a for loop. I use while loops personally, but you can set up a while loop to go ahead and keep doing something until you get the result you want. Whereas in your calculator, I don't think any of your calculators can do while loops. Maybe I'm wrong, but I don't think you can. So that is the huge reason why I really suggest MATLAB, because of that iterative process with the sequential linearization. But if you remember from math, you can use a Taylor series expansion. And as long as you're relatively close to a desired solution, you can throw out any of these higher order terms. So essentially what I'm saying here is, if you want to solve for the solution of f of any x value you want, and that's not the correct answer, f of x plus h, so you're off by your final answer, that gives you your correct answer, the f of xk. But then you get that h term in there. So then you got to take the first derivative with respect to x times h, and then you do the second derivative times h squared, the third derivative, fourth derivative, fifth derivative, and on and on and on. But because we're trying to use sequential linearization, we want to throw out our higher order terms. So if we're close, we can say that our equation there is just f of xk plus df of xk times h, and that's it. And that's a linear system. Y equals b. Normally we say mx plus b, but to match it with the Taylor series expansion approach, it becomes b plus mx. And when we get the exact solution that we want, we're going to do for root solving. So we're going to plug in this value at the exact solution, and our result is going to evaluate to 0. Okay. So our f of x, when x is the exact solution, is going to be equal to 0. And so here's the graphical approach. So, and this is just the equation f of x squared minus 2. You can see it crosses the x-axis, but it's just a parabola. That's increasing. So I'm going to pick an operating point, and my first operating point, or my first point, is going to give me an x there. So essentially what I've done, whoops, I'm way off. I'm picking an x value. That's my guess. I got to start off with a guess. I have no idea if that's right, but I hope it's relatively close. That's my guess for my answer. Then I plug it in here and ask the question, does it equal 0? In this case, it does not. It's way beyond 0. Okay? So what I need to do now is I need to take the Taylor series expansion and get this delta y, delta x. So now I can find a new point, a new input value to start. Once I have that value to start, then I'm going to plug that value into my f of x equation and check again. Does f of x here equal 0? It does not appear to do it in this one. So again, I'm going to take the slope of the line and find my next intersection point. And the hope is I'm going to get closer and closer to 0. The problem with solving nonlinear is you never actually get the 0, right? You can never get there from here because you keep, getting closer and closer, but the slope never gets to 0. And the other problem with this is you have to be reasonably close to your final answer. If I had picked a starting point that would have resulted some way up over there, I might have completely missed the value that I started with. I might not have had any chance whatsoever to go ahead and do that. So this is the sequential linearization, is calculating a new slope at every point when I start my iteration. And so this is the process, right? For an initial guess, right, we'll call that our initial iteration. We're going to go ahead and update our value of x based on solving for this delta x. How do we get delta x? We do our Taylor series expansion, which means we're going to solve for that equation right there. And then we're going to pull out our delta x. So our delta x equation is just going to be the first derivative of our x equation. And this is evaluating at that x of v. And notice it says x of v because that's an iteration. I got to keep track of each iteration. So that I'm evaluating the derivative of f of x at that value. I multiply it by my f of x at that value, and then I end up with a number. I take the negative of it because I set this equation equal to 0, so I'm solving for that. I've got a negative value there, and then I update for my next iteration result using that delta x value. And then I rinse and repeat until such time that f of x, and we'll call this actual, is approximately equal to 0. Okay? Approximately, not exactly equal to 0. All right. Let's do like your calculators do. Let's write a program, or let's figure out how to solve for f of x equals x squared minus 2. We already know the answer. X equals plus or minus square root of 2, right? We can do that algebraically, but your calculator can't do that. It has to be able to figure out the numbers. So now what we need to do is we're going to write f of x. And what is the derivative of f of x with respect to x equal to? It's just 2 times x, isn't it? First derivative of x squared is 2x. First derivative of negative 2 is 0 because there's no x value in there. So we now have the derivative of f of x, or f prime. Now we're ready to start dumping into our delta x equation. So my delta x equation is going to be 1 over 2x, and then I just added the v term in there because, again, I'm iterating that value. And then I multiply by the f of x value. or f of x equation, again, evaluated at that specific iteration value. And then once I have that, I rinse and repeat. So I add my delta x, and then I basically go back through the process there. However, I can add that all in one fell swoop, doing it right there. So let's do that by hand. So we're going to start out with 1. We'll just guess 1. And the very first thing we do, does this equal 0? So we plug in an x equal to 1. We check f of x. Does it equal to 0? Not even close, right? That's -1. That's nowhere near that value. Now we should have said, all right, well, it's not anywhere near 0. So let's go ahead and find delta x so I can update my previous x value. So I solve for delta x, which is right over here, right? So let's plug that in. Let's actually show the work. So f of x is equal to x squared minus 2. And f prime of x is equal to 2x. So we'll plug in the number 1. So x squared minus 2, 1 squared minus 2 minus 1. F prime of x, 2. So 1 over f prime of x is equal to 1 over 2x. So that's equal to 0.5. Now my delta x, I'm going to go in and calculate what my delta x is going to be. My delta x is the negative of this term. So we'll call it f of x times f prime, 1 over f prime of x, I should say. So let me just write it this way. And it's the negative of that. So -1, right? Over or -1 over 2, and I have to have a negative number, is equal to 0.5. So a positive 0.5. So that number here gets added to the previous value. Then we do that again for 1.5 and check and see if that result is correct. So instead of doing it by hand, I've got a very simple, basic MATLAB script file that does that. So here is my equation. F of x equals x squared. And you can see I put that in on the first row as just the value. So I have f of x equals x squared minus 2. That's just a comment, right? You can see the parentheses sign there. Then I'm going to go ahead and start with my value of x equal 1. And you'll notice I put dx equal to 1 in there. Anybody want to guess as to why I put the dx equal to 1 in there? I should have calculated it, but why did I specify dx equal 1? No, technically I don't even need it, so I'm just going to delete it. So let's ignore that. Now I'm going to set n equal to 0. So I'm just keeping track of my iterations just to see how long it takes. And now this right here, this says while the absolute value of x squared minus 2 is greater than 1 micro, and my Sn is less than or equal to 100, do the following. The abs of x squared minus 2, that's f of x. That's supposed to be 0, right? So if it's greater than 1 micro, to me, that's not close enough to being 0. So I want to go through and update my value of delta x every time until that's pretty darn close to 0. I also ANDed it, right? So both of those conditions have to be true. N needs to be less than 100, and my f of x has to be less than 1 micro. The reason why I added that n is less than, or if n is greater than or equal to 100, or I should say it has to be less than or equal to 100, because you screw up with code all the time. So instead of ending in this perpetual loop that just keeps running and running and running forever, if I've made a programming mistake, if I got a negative instead of a positive, then that stops it at 100 iterations. And so if you're going to do MATLAB code where you're going to be doing iterations, I strongly encourage you to have an iteration counter and to stop your loops after a certain period of time, because it's not going to be converging to a good result. So here's my f of x. I've got my f prime of x, which is 2x. My delta x, which is -1 over f prime times f. I update my x value. I increase my iteration counter. And then I go back up and do it as long as that absolute value is greater than 1 micro, and my iteration counter is less than or equal to 100. So I'm going to go ahead and run this, but I'm going to set a breakpoint. I'll set a breakpoint right here. All right, so let's run it, and let me slide this over so maybe we can see. What MATLAB is telling us. Where's MATLAB? Guess I have a lot of things open. Okay. All right, so first iteration. F we said is equal to -1. F prime, 2. My delta x is equal to 0.5. And now I've gone through and said, you know what? I'm ready to update my x value. So you can see that my x has gone from 1 to 1.5. Now I'm going to continue. See if I can move this out a little bit. And go to my next iteration. So you're going to see that n increases to 1. Then it's going to go back up and do the whole calculation over again. Now it calculates f being 0.25, which is good because it started out at -1, and now it's at 0.25. So the absolute value is closer to 0, right? 0.25 is a lot smaller or closer to 0 than -1. So that's a good thing. I'm getting closer. My f prime value is 3. My dx is also good because it started at 0.5. Now it's -0.0833. So it's almost an order of magnitude smaller. So I'm taking less large jumps to get to that final answer. That's the sequential linearization. I'm linearizing every time, so I don't have fixed steps to get to my final answer, because the fixed steps will probably mean I'll overshoot. So now my x value, instead of 1.5, now it's 1.4167. Now, is that less than the error? Or the f of x value, is it less than 1 micro? Well, let's check. It's not. It's 0.0069, so it's going to iterate again. Notice my dx, it was 0.0083. Now it's 0.0025. So about a quarter of what it was before. But let's check and see if that's less than 1 micro. Not quite. It's 6 micro. It's still a little bit too big for the rules that I had. So let's keep going. Now I'm at 1.414. Let's check again. Oh, it's done. It finished. So let's run it again. And here is our final answer. 1.4167, which, if you ask MATLAB, what is the square root of 2? 1.4142. So we didn't get exactly to 0. We got pretty close. How do you get closer and closer to 0? Instead of saying 1 times 10 to the -6, let's go 10 to the -12. It's going to take longer for us to get there because we're doing more iterations, but let's see what we get. So one more iteration, look what we got, 1.412. Oh. Which is pretty darn close, at least we can display. So one additional iteration over got us really, really close. And you can even do more precise and go ahead and do that. What happens if we do this problem and instead of starting at 1, let's say we start at 1,000 because we have no idea where to start. Notice the number of iterations it took to get pretty accurate is 5. Let's rerun that. Still got to the same answer, but look how many iterations it took. It went from 5 to 17 iterations. So being far away from your number, your final number still could get you there, but it can take a long time. And when you're trying to invert a million by a million bus with complex numbers, that takes a lot of computing power. What if we started at, whoops, I started at 1,000. That was not the iteration. I guessed 1,000. What if we guessed -1? What do you think will happen with -1? Is that close to the answer of square root of 2? Not close, is it? Closer than 1,000, but not close. Well, let's run it and let's see. Took 5 iterations, but look where it got me. It got me the other valid answer. It got me the other number, negative square root of 2. So depending on which side you are, right, it can get you to one answer or the other. Nonlinear answers, nonlinear systems, the possibility is they can have very many valid solutions, but not one that you would perhaps want. So again, your initial guesses are crucial to making sure that you're going to get a reasonable result. Okay, questions on that? Because I actually have another one, which is the same equation, but one tiny little tweak. Do you remember how I said before, x squared plus 2 has no real solution? Let's see if Newton-Raphson can solve it. So let's minimize this. No valid solution. See how it got to 101? N is equal to 101? That kicked me out. It stopped it. So if you have complex numbers in here, Newton-Raphson won't work. So you couldn't do Newton-Raphson to get a complex number. And that proves it here. Even if you look at it, hey, look, we got good numbers and all that stuff. Newton-Raphson does not work for complex numbers. You cannot do complex numbers. Yes, sir.
What do you mean by take you out? But does MATLAB stop working?
Take Q out?
Instead of like take you out.
Oh, no, MATLAB kept working, but if you remember, I had an iteration counter saying n has to be, 2 conditions have to be met. F of x has to be less than 1 times 10 to the minus 6, or n has to be greater than 100. So my f of x, I still think is too big. I can even type that in here. It's 9.5746. That's much bigger than 1 times 10 to the minus 6. But I've already gotten to over 100 iterations. So at that point, it's like, I'm not getting there. It ain't going to work.
But then you put like a cover there and keep going.
You want to go 1,000? Should run. Went to 1,001 iterations. So if you get a complex number, you can run this for infinite times and it's never going to get there. Just won't get there. So why does that complicate things for us? Because when we talk about power systems, we have P plus JQ. We have a real part and an imaginary part for our impedances. So one of the things that we're going to be doing when we start writing our equations is we have to start stripping out the real parts and the imaginary parts and isolating them into separate equations so that all the numbers are real, but then we'll just have to keep track. Is this real or is this reactive? And go from there. We'll actually do magnitudes and angles to make it work, but you'll see how that works once we get into that. So what I've got right over here is basically my for loop. Or while loop. While this is happening, do the following. And we even saw, right? We saw how the error decreases quite quickly, right? We started at a 0.5, then we moved to like 0.83 or minus 0.83 or 0.083, I can't remember. And we're driving our result to 0. You stop it when this value of E, and you pick the value of E, that's your error that you're allowed to. Is it 10 to the minus 6? Is it 10 to the minus 12? You can certainly go up a lot more precision. The problem is if you go higher precision, then it takes more iterations. And how accurate is it going to be, right? Like when you do a transmission line model, it's not accurate to 17 digits. It's going to be accurate to 2 or 3 digits. So you don't want to put insanely high precision values in there because you're probably not going to get really good results for the amount of processing power you need. And as we said, it's so important, the initial guess. We tried -1. What if we had tried 0? 0 seems like a valid number, right? Let's check it out. Not a number. That's because 1 over 2x, when x is equal to 0, is infinity. So again, you can even pick numbers that seem reasonable that are going to blow up in your face. So picking the right number is essential. But again, in power systems, it makes it pretty easy for us to go ahead and do that. So I think that was my last slide. Questions on, this is what we call single variable Newton-Raphson load flow. It's the simplest one. We're going to be doing multivariable because remember, we have many, many variables in our system. We're going to be moving to multivariable. The other really challenging part about this is for the most of you as college students, this is probably the only time you're ever going to have to solve nonlinear equations using math. Like we said, when you do a power electronics, right, you just pick a Q point. Some of the more updated technologies, but we don't really use them in power systems. There's a couple of reasons for that, but the other ones, the old methods work really well. And they also tell you some additional information about sensitivity. It's called particle swarm. It's the idea if you have 100,000 ants and they're all trying to get food in a certain location, they'll all congregate in one area. And if you run that 50,000 times, the area that they most likely end up is the highest rate of survival. So basically, it's like brute force. If you just run millions and millions of simulations and see what the voltages would be, that would work for you. But there hasn't been a lot of research into using that for power systems. This works pretty effectively. We also have a lot better processing power. And for the most part, when you do power systems analysis, like the company I've done consulting with in the past, they have, I don't know, 30 computers that are networked together. And then they use specialty programs to basically have these computers that are being lightly loaded. They'll just dispatch them to do a bunch of different work. And so it used to be like you had a supercomputer that would be built with 50 computers that were dedicated. Now you can have software running in the background that checks what their workload is, and then they can siphon off and give them their processing, their processor a small bit of work, and then it'll combine it at the end. And so a bunch of companies can do that. I can't remember the name of the product that the company that I consulted with, you would use, but they would still run load flow analyses that would take a day, 8 hours. So once you hit simulate, you better know that your inputs are correct, or else you're going to get garbage out after a day. And it's really, really frustrating. But as processing power improves and we network our systems together, it makes things much more effective. Okay, any questions on introduction to load flow and power systems? Because the next class, we're going to do multivariable, which means we're going to have to do partial derivatives. So I mentioned that a little bit. And then in the third class, we're actually going to apply it to power systems. So we have to write, right now I gave you f of x equals x squared minus 2. By the end of this chapter or this section, you're going to have to figure out what f of x equals. So not only will you have to figure out the variables that you need to solve for, those x's, but you're also gonna have to figure out the f of x equations that you need to solve to check. And so what we've done is for nonlinear, your f of x is x squared minus 2, and we set that equal to 0. So you have to have a way of checking, is my answer right? Is the square root of 2 a correct answer? We'll plug it back into the original equation and see if it works. Square root of 2 squared minus 2 does in fact equal 0. So anything nonlinear, you've got to have an equation to check to make, and a way of checking to make sure that your answer's right. And so we'll be doing that at the end, not next week, but the week after, because Monday and Tuesday, you all have the day off, right? So no lab on Monday and no class on Tuesday. RD, right? That's all I have. Have a great 4-day weekend, 3-day weekend, whatever weekend you have. And yeah, take care. Hold on, let me stop.
Thanks, Paul.
Thank you.